Okay, so last day we had been discussing about uh, two different setups in which we could ensure fairness in a uh, binary classification task, and one was where we were trying to maximize accuracy under fairness constraints, and the second one was maximize fairness under accuracy constraints. Now, for the first one, we had written an expression as follows: minimize subject to so this was our first setup, and in the second setup there we wanted to maximize fairness. Such that, or subject to, L theta less than equal to 1 plus gamma L theta star, where L theta star is the loss function of the unconstrained classifier. Now, one can have a further fine-grained version of this particular objective function, and this is what the authors call the fine-grained accuracy constraints. Now, what does this mean? So, if you look at classifiers like LR, SVM, you will observe that the loss function is additive. Usually, the type of loss function that is used, they are additive in nature. Now, by this I mean that L theta can be expressed as a simple linear sum of Li theta. Okay, for each data point, the loss function can be individually computed. Okay, so now rather than trying to put the constraint on the entire set, okay, one can also try to put the constraint on a selected set of data points. Fine. Now, how do we do that? So, the formulation remains very similar. You minimize, oops, sorry, here also you minimize. None of you pointed out. Because covariance you need to minimize. Covariance 0 means we have maximized fairness, right? That's what we studied last day. Okay, so minimize the same covariance. See, sometimes I'm writing d theta xi, sometimes I'm writing theta t xi. These are interchangeable, they are same. Okay, so subject to, now you have individual constraints. Li theta less than 1 plus gamma I Li theta star for some chosen values of I to n. Okay, so Li theta star is the individual loss associated with the data point I. Okay, so this is the individual loss associated with the data point I for the unconstrained classifier. Okay, now think of the case of simple LR. We know theta star is argmin theta okay, so individual Li theta will be nothing but minus log p yi xi theta, because it's a simple addition. The losses are simple addition of the losses on individual training data points. Okay, now if we set for a particular data point, say for a data point I, if we set gamma I equals 0, then what does this indicate? What does this indicate? If I said gamma I is equal to 0 in this equation, for a particular data point I, if I said gamma I is equal to 0, what does this indicate? So it tells you something about the ith user. Okay. So the probability of the ith user being mapped to the positive class is than the unconstrained classifiers. So what should be the blank? Put gamma equals 0 in that. Yeah.
Higher or equal.
Yes, higher or equal. Okay, because loss is lower or equal, so therefore putting it in the positive class, that probability is higher or equal. So loss lower or equal means putting it in the positive class, that probability should be higher or equal. Okay, so try to remember this connection between loss and the positive class mapping. Now, why do you think that this fine-grained constraint is important? Any necessity? Excuse me. Do you feel that there is any necessity of this fine-grained constraint? Start from thinking about the problem that you have at hand. You have a data set to be classified. Okay. Now, in this data set, you have a sensitive attribute. Let's say z equals 1 means unprotected, and z equals 1 means protected. Okay. Now, then, like, why do you think that this fine-grained classifier is at all of any need? So we could have done with the like aggregate constraint. Why is this fine-grained constraint at all important? Thinking from the perspective of the problem that you have at hand. So basically, this came to the author's mind because something was going wrong, right? Can you figure out what was going wrong when they were setting the constraint to be one single integrated constraint?
So I think the considering the sensitive attributes for some set of users, we can distinguish the loss. So if there
Yes,
is,
good. Distinguishing the loss is important, but why do you think is distinguishing this loss important? You are you are on the right track, but distinguishing this loss is important for a particular reason. Think from this perspective: z equals 0 and z equals 1, and their belongingness to the positive class. Now can you think of
It might help to prevent the mistake that is done by the constant optimization, I think.
What kind of mistake are you talking about? This is what I want to come to. What is the mistake? What is the exact mistake? Okay, let me portray the picture. Suppose you have the unconstrained classifier. Let us call it UC. Okay, and then there are some users who do not have the protected attribute on, and there are some who have the protected attribute on. Okay, now among these, some of them have been identified in the positive class. Okay, and some of them have been identified to be in the negative class, and also among these, some of them have been identified in the positive class, and some of them has been identified in the negative class. Now you are putting a constraint on this UC. Okay, now you are bringing a constraint. What can this constraint do?
The constant one can by mistake classify the positive one into negative, where the originally the unconstant classifier classified that particular individual as the positive, but the constant one might classify as negative.
So who will be more hampered? Z equals 0 or Z equals 1 in this particular case?
I think the protected one.
Think carefully. I want to spend some time on this. Others also think. So these kind of thought processes are what this course is mostly meant about. See, what is this constraint trying to do? Some sort of rebalancing. Okay, some sort of rebalancing of the positive and the negatives. But then in the process of this, what can happen is that you might, so after putting this constraint, what might happen is that for Z equals 0, those who were positive and really positive, okay, those who are classified positive and really positive, they can be pushed to negative in order to make space to admit more from the Z equals 1. Okay, but this should not happen. We should not compromise those cases that were actually positive and also classified as positive for the Z equals 0 category. Okay, those should not be hampered. Okay, now the total constraint that you see there, that can hamper the overall like predicted level of these guys. However, if you specifically use the loss for each and every single data point, then we will have the freedom to include the constraint for only those data points for which we are actually concerned about. Okay, we do not need to consider all the data points while obeying this constraint or while adhering to this constraint. Those that we want to select, we can select, we are free to select because these are individual loss functions. So therefore, we can individually select each of the data points on which we want the constraint to be maintained, okay, rather than having one single global constraint on the whole data set, which might adversely affect the unprotected group members who are actually supposed to be positive. Okay. Now, you know what is this called? If this kind of a situation arises, what will happen? This is reverse discrimination. So basically, in order to remove the discrimination from one set of users, you are introducing additional discrimination for the other set of users, which is not desirable. So that is something that one needs to take care of. And therefore, one needs to have the liberty to apply the constraint on individual data points rather than applying it on all the data points as a whole. Okay. So do you see this? Make sense? Okay, if it doesn't make sense, then also you can ask questions. Please tell me if it makes sense or not. Hello? Hello?
I can hear you, sir.
Yeah, so does this make sense
Yes, sir.
for the others? See, let us interact uh, like if we don't interact much, like it will be difficult for me to understand what are the things that you are not able to grasp, or if you are able to grasp everything. So a little bit of response at some point in time might be nice to have. Okay, so uh, so basically, again, just summarizing, we have under the um, accuracy constraint, we have two types of constraints. One is the general one, general, or let's call it aggregate level. And the other one is the fine-grained one. Now, in the aggregate level, you try to apply the constraint on all the data points equally, okay, which has this problem, potential problem, that some of the unprotected group members can suffer from reverse discrimination. Whereas this problem gets resolved here because now the constraint can be applied to only our chosen set of data points. Okay, so this is overall, in a nutshell, the different formulations that the authors actually prepared for their experimental validation. Now we go on to the experiments. They use two types of data sets. The first one is a synthetic data set. So in order to understand like empirically what is going on in the data set. So okay, so like if I generate a data set with certain properties, whether when I apply my constraints, certain specific things happen on the classifier, which connects to our intuition of imposing fairness. Okay, that is what they are going to show in this particular part of the experiments. And then they have real data sets where also they will show the success of their model. Okay, for the synthetic data set, we need on one side labels and the other side features, right? So we need labels as well as we need features. So for generation of labels, what the authors did was they sampled 4,001 labels uniformly at random. Okay, they sampled 4,001 labels uniformly at random. Now, why uniformly at random? Why uniformly at random? So that half of the labels and the other half is one. Okay, so that is what they did for generating the class labels. Okay, now they have to generate the features. Getting responses like, are students there in the class? Yeah, okay, quite a few are there. Just wondering like, okay, fine. Okay, so half of the labels are 0 and half of the labels are 1, so approximately. Now for features, what they did, they constructed a two-dimensional feature vector. Okay, for every label. And these were drawn from two bivariate Gaussian distributions. So P x y equals 1 is okay. Let us call it -1 and 1 for the sake of better clarity. Half is -1, half of the labels are -1 and the other half is +1. Okay, so this is the first one, and the second one so you know what are these? Anyone knows what are these?
Mean vector and covariance.
Yes. So this is the mean and the covariance of the Gaussian distribution that they are using. Okay. So the first one has a mean of 2. Okay. For the two variates, it's a bivariate. Okay. And the covariance matrix looks like this. The other one is like sufficiently opposite. Okay. And the covariance matrix looks like this. Now they sample like all the positive samples from this distribution. Okay. And they sample all the negative samples from this distribution. Okay. So this is how they construct the feature vectors for the positive and the negative class. Now, next is the sensitive attribute. For computing the sensitive attribute, z equals 1, okay, is computed as follows. X bar okay. So what is this? A Bernoulli distribution. Now, P z equals 1 is drawn from a Bernoulli distribution like this. Okay, where we have to still define x prime. What is x prime? X prime is nothing but what is this? What kind of a matrix is this?
Rotation matrix.
Rotation matrix. So this rotates the original feature vector. Okay, and depending on theta, okay, depending on theta, you have the intensity of rotation. So the intensity of rotation is dependent on theta. Okay. So now the authors tested for two different theta values, for two different rotation values, pi by 4 and pi by 8. Okay. Now tell me theta tending to 0. What does this mean? Theta tending to 0 means put theta equals 0.
It will be identity, no rotation.
It will be identity. So it will be exactly same as x, right? So what does this mean? This would mean theta closing to 0 means z is highly or less correlated. So that means in this equation you will have x prime will be replaced by x. Okay. So px y given 1 by px y given 1 plus px y given minus 1. Okay. So this will be, so pz equals 1 is the sensitive attribute. It is less correlated or highly correlated.
It will be highly correlated.
Highly correlated because pz equals 1 will become proportional to, forget about the denominator, will become proportional to px y equals 1, right?
Yes, sir.
So this will be highly correlated. See how they are designing the experimental setup. So like when you do your term projects, you will also have to go through all these type of experimental setups. Of course, not for all of you, but for some of you who are doing this kind of problems, you will also have to go through this kind of experimental setup. So now you have two things. One was the C. You remember the C? The C in the constraint. In the constraint, which we call the covariance threshold. This is one thing. And so we have, so as if you can imagine that we have two hyperparameters in the system. And one is the theta, which is the intensity of rotation. So remember that what the authors are doing, they are basically introducing the Z attribute by giving a simple rotation they are introducing the Z attribute by giving a simple rotation to the feature vectors. Okay, that is what they are kind of doing. So remember this, because our results will like will be interpreted based on this particular intuition. Okay, so as soon as we see the result, we will probably be able to connect the this intensity of rotation or this introduction of the z variable uh, through the rotation of the feature vector and the way the constraint of the fair classifier is working. Okay, so we will see this. So as soon as we see the results. Okay, so these are the two hyperparameters. Again, if C is closing to 0, then this means highly fair. Okay, so now let us go and see the results that the authors got from this particular synthetic set of experiments. You are able to see this, right? Can you please confirm?
Yes, sir.
Okay,
Yes, sir.
fine. So now the first one, that the first set of experiments that we are seeing here is where you have maximizing accuracy under fairness constraint. Okay, so maximizing accuracy under fairness constraint. So now this line that you see here, the bold line that you see
Are you
here,
showing any result or figure? I'm not able to see that.
nobody is able to see it.
No, sir, it's not visible.
Oh, oh, somehow the screen sharing has stopped. I don't know why. But you are able to see my notes, right?
Yes, sir. It's stuck on the PZ equal to 1 equation.
Okay.
Like the sensitive attribute equation, the Px dash y equal to 1, that one we can see currently.
Oh, but here it's telling. Okay, let me stop presenting and present again. Now you're able to see the screen, hopefully.
Yes, sir.
Okay, so let us go back. This part you have seen.
Yeah.
This part is okay, right? So you
Yes, sir.
have two hyperparameters in the system. One is the theta and the other is the C. Okay, so now we will see the results that the authors have obtained. Now tell me if you are able to see the results.
Yes, sir. It is visible now.
Yeah. So now, so the first set of results that we are seeing here is when you are maximizing accuracy under fairness constraints. Okay, that is the first type of optimization. So here, this bold blue line that you see here, okay, this one is the unconstrained classifier. Now, the other two that you see here, the other two broken lines that you see here are the constraint classifiers, okay, for different values of C. So this P rule actually corresponds to different values of C. Okay, so this is the unconstrained classifier. where the P rule is 45%, which is not satisfied. Okay, if we consider the 80% rule, here it is 70%, like, which is still okay. Of course, there is a little bit of accuracy compromise. And then, like, if you make it too high, then the accuracy drastically drops. Now tell me what happens in this space. Can you see something interesting? So this is for theta equals pi by 4. Okay, I was telling theta, they are calling it phi anyway. It's the same thing. Any observations that you can make? So how has the classification boundary changed? When you put the constraints, these are the constrained ones. When you put the constraints, constraint boundaries, how has the boundaries changed? What has happened to the original boundary? If you consider
It has rotated like.
it has rotated. Very good. It has rotated. Okay. And where is the rotation higher? Larger C, larger rotation. Okay. So this is the larger C. This one. Larger C. And it undergoes larger rotation. Fine. And this one is the smaller C. So it undergoes smaller rotation. Sorry. So basically, like, what I want to mean is that you want to, like, have larger P% rule. That means a more fair classifier. That means like a smaller C. Lower C, higher rotation. Okay. So this has the lower C and this admits higher rotation. Now, the important point here to note is, why is this rotation happening under the constraint? Why do you think that the plane rotates or the boundary rotates? Why rotation? Why has the boundary rotated? No idea. How did we originally construct the sensitive attributes?
Rotating the feature vector.
By rotating the feature vectors. So therefore, the classification boundary also has to rotate and align itself so that, so under the constraint, so the imposing of constraint actually rotates the classification boundary accordingly so that the correlation with the class labels do not affect the classification. Okay, so we said that if there is high correlation between the class labels and the sensitive attribute, then it is not a desirable thing. Okay, so and therefore we imposed constraints based on the extent of correlation. We imposed constraints and we tried to like re-rotate our classification boundary in such a way so that this particular undesirable situation does not arise. Okay, so same is the case for pi equals 8. Again here there is a rotation, but then here you have even larger rotations, right? Why? Why are the rotations even larger? What did we see? If this tends to 0, which one is small among these two? This one, right? So here the correlation between the sensitive attribute and the class labels is stronger. So therefore, a larger rotation is required to actually remove this undesirable effect. Agreed?
Yes, sir.
Yeah. So this is one part. Tomorrow we will study the other part and also we'll talk about the results on the real data set. So this is maximizing accuracy under fairness constraints. We will also do the other one, which is maximizing fairness under accuracy constraints, and we'll see how the results look there. And then we will go to real data set experiments.